Okay, so what if I told you that you could run a cutting-edge AI, the kind that usually needs a massive supercomputer, just by using a whole bunch of regular computers all connected over the internet? Well, we're going to dive right into that because a team of researchers has figured out a pretty groundbreaking way to do exactly that.
So to get started, just take a look at this number, 350 gigabytes. What do you think that is? The install size for some crazy new video game? Your entire photo library going back to college? Well, it's actually something way, way more demanding.
Yep, that's how much RAM or system memory you'd need just to load one of these huge open-source AI models like Bloom. Now, to put that in perspective for you, your high-end gaming PC might have 32, maybe 64 gigs if you're lucky. We're talking about a completely different league here. And this really highlights the core problem we're facing.
Which brings us to what's called the billion parameter problem. This is really all about why the most powerful AI has been locked away from, well, pretty much all of us.
So here's the deal. As AI models have gotten smarter and more capable, they've also gotten absolutely gigantic. We're talking hundreds of billions of parameters that all need to be loaded into memory at once. And look, this isn't just some small inconvenience. It creates this massive wall that locks out students, independent developers, and even researchers at smaller schools from getting their hands on the best tools in the business.
But what if we could just tear down that wall? And that leads us to this really radical idea, an AI for the people. What if we could just share that huge workload across the internet?
Okay, so check out this diagram from the actual research paper. It shows the whole concept perfectly. Instead of having one monster computer trying to run the whole show, you just break the AI model down into all of its different layers. Then, you hand out those layers to a whole network of different computers. The researchers just call them servers. Each one handles its own little piece of the job and then passes its work on to the next computer in the line.
This whole clever setup actually has a technical name. It's called distributed inference. But really, all it means is you're getting one single massive AI model to work by splitting up all the hard computing work among a whole bunch of different machines that are all connected to each other.
A really great way to think about it is like you have a global team of volunteers, and you're all working together on one of those giant 1,000-piece jigsaw puzzles. No one person has to figure out the whole thing. You just get a few pieces, you figure out where they go, and you connect them to what your neighbor is doing. And by everybody working together, the whole team finishes this massive puzzle. It's a really powerful idea, but, and it's a big but, it comes with an equally massive challenge.
And that brings us to the biggest hurdle of all, surviving the good old unreliable internet. How in the world do you build a system that you can count on when it's made of parts you can't?
Let's be real. The internet can be a messy and unpredictable place. So you're facing two huge problems here. First, these volunteer computers, they can just vanish. Someone shuts their laptop, their Wi-Fi cuts out, and poof, the whole chain of computation is broken. Second, you're dealing with all sorts of different hardware. My 10-year-old laptop is not the same as your buddy's brand new gaming rig. And that creates these bottlenecks, where the entire process just grinds to a halt, waiting for the slowest machine in the chain.
So how do you solve a problem like that? The key is this really brilliant engineering concept called fault tolerance. All it means is that you design a system that actually expects things to fail. It's built from the ground up to recover from problems smoothly without having to just throw away all the progress it's made and start all over again from the beginning.
And check this out. This is how they actually do it, broken down into 4 steps. So first, the client, that's you, the user, is running the show, and it notices that one of the servers in the chain has just disappeared. Second, it immediately sends out a message, asking the network for a replacement. Third, and this right here is the magic trick, a new server jumps into the line, and the client gives it the last known good state of the calculation from its own memory. And finally, the whole process just picks up and keeps going seamlessly from the exact spot where it left off. No starting over. It's brilliant.
Okay, so the theory is super elegant, right? You've got this smart, self-healing system. But that brings us to the most important question of all in our next section, putting the swarm to work. Does all this cleverness actually hold up in the real world?
I mean, this is really what it all comes down to, isn't it? We've seen all this smart engineering, but is the final system actually fast enough and reliable enough to be useful for anything? Or is it just a really cool science experiment that's too slow for anybody to actually use? Well, the researchers put it to the test, and the results are pretty stunning. Just look at this table. This shows a simulation where 1% of the servers are constantly failing, so a pretty shaky network.
A normal system without this smart caching thing just crawls along at less than 1 step per second. But their method, it's blazing past at almost 8 steps per second under the exact same chaotic conditions.
You know, sometimes a table just doesn't do it justice. You gotta see it visualized, because the difference is just staggering. On the left, that little bar, that's the system that has to restart every single time something fails. And on the right, that's this new fault-tolerant method. I mean, it's not even a competition.
So here's the bottom line. Even in this really volatile environment where computers are constantly dropping out, this new method is nearly 9 times faster. What they've done is effectively transform this messy, unreliable network of volunteers into a single, reliable, high-performance machine.
And get this, this wasn't just some clean little simulation. They ran a real-world test with that enormous 176 billion parameter BLUE model. They built a working network with servers stretching across 2 different continents, with all the internet lag and messiness you would expect. And the result? The system performed more than 10 times faster than the traditional ways of doing this. It actually works.
The fact that this experiment was so successful is just incredibly exciting. And it brings us to our final section here, the future of shared AI. Let's talk about why making this technology available to everyone really matters.
Look, what we've just walked through today, it's not just some clever trick. This research offers a real, concrete blueprint for running the world's most powerful AI models as a giant team effort. It means we might not have to depend on just a handful of giant tech companies and their private supercomputers to push the boundaries of what's possible with AI.
And just stop for a second and think about what this unlocks. It gives researchers at any university the same powerful tools as the biggest labs on the planet. It lets individual developers and tiny startups build amazing new things we haven't even thought of yet. And ultimately, it just helps create a more level playing field for innovation, where the best ideas can win, not just the ones with the biggest budget for hardware.
So I'll just leave you with this question to chew on. This kind of technology points to a future where all that immense AI power isn't locked away in some data center somewhere, but it's accessible to anyone with an internet connection. So, what would you create if a supercomputer was available to everyone?